Hi everyone, welcome back to another video of our Ethereum series. In this video, we'll discuss dApps in detail. So, dApps or decentralized apps are a combination of smart contracts and a UI. So, basically, the developer will write a smart contract and deploy it on a blockchain network, and then they'll also deploy a user interface on some service, and it interacts with that smart contract using some supporting library like web3.js. So there are many dApps out there like Uniswap, Compound, Aave, InstaDapp, etc. There's actually a site called Dapp Radar where you can discover many dApps. So you can go to explore dApps, and you'll see many dApps deployed on different blockchains like Meta1 is deployed on Ethereum, Hot Game is deployed on Near. So you have a list of many dApps deployed on different kind of blockchains. You can see that this World of Typians is deployed on Ethereum, BNB, Nebula, Base, and Core. So do check it out. Do take out some time and play around with this website. It will help you understand what kinds of dApps are there available on different kind of networks. So coming back to dApps, dApps are a combination of smart contract plus UI. Uh, I'll show you an example. For example, this is a Uniswap. So this Uniswap dApp has its UI deployed somewhere, and we can sell some ETH in exchange for some USDC. We can connect our wallet and make a transaction from our account. And behind the scenes, it will call the Uniswap contract that is deployed on the Ethereum network. Similarly, we have Instead app that it is a money management kind of platform where you can manage your portfolio and get the best DeFi yields. So it works on a similar principle that the UI is hosted here, and whenever you make a transaction on this UI, behind the scenes, the smart contract of Instead app is called on the Ethereum network. So let's talk about the features of dApps. dApps are decentralized, deterministic, Turing complete, and isolated. Decentralized means that dApps operate on Ethereum, which is an open, public, decentralized platform where no one person or a group has control of it. Deterministic means that dApps perform the same function irrespective of the environment in which they get executed, which means if you are executing some kind of operation, you can pretty much predict that this and this will happen. dApps are also Turing complete, which means dApps can perform any action given the required resources. Now, Turing complete is a completely separate concept, which is a way to describe the capabilities of computer systems, programming languages, or any other computational device. In layman terms, a system is Turing complete if it can, in theory, perform any calculation that any other programmable computer is capable of. Essentially, this means that the system can simulate any computer algorithm, no matter how complex, given enough time and memory. The last feature of dApps is that they're isolated, which means dApps are executed in a virtual environment known as EVM, so that if the smart contract has a bug, it won't hamper the normal functioning of the blockchain. So, whenever you execute a transaction request on the blockchain, the state changes are carried out in the EVM according to the code of the smart contract, but in case the transaction fails, those state changes are not committed on the blockchain. Now, what are the benefits of dApp? We have a few benefits of dApps, which is zero downtime, privacy, censorship resistant, complete data integrity, and trustless computation and verifiable behavior. Let's try to understand each of them one by one. So dApps have zero downtime, which means that once the smart contract is deployed on the blockchain, the network as a whole will always be able to serve clients looking to interact with the contract. Any malicious actor, therefore, cannot launch a denial of service attacks targeted towards individual dApps. Now, that is a benefit mostly in theory because it really depends on the underlying blockchain network. For example, the Solana network is down often, so you are not able to access dApps, or the cost to access the dApp is very high. In Ethereum, also the cost problem is there because Ethereum has low throughput, low transaction per second. So if too many transactions are happening on the network, you have to pay a lot of gas fee for a very simple transaction. Like simply transferring some ether should cost you around $1 or $2, but in times of heavy congestion and heavy usage, you might end up paying $100 as a gas fee just for transferring $1 from one account to another. So you'll see some difference between the theory and reality on this aspect. The next benefit is privacy. You don't need to provide real world identity to deploy or interact with a app. So you can just create a MetaMask wallet and you can deploy a smart contract code using that wallet, and your identity won't be there anywhere on the Ethereum network. So that way you don't really have to reveal your real world identity. But again, comparing the theory versus reality, whenever you are deploying a dApp on Ethereum network and you want to promote it among many people and you want many users to be there for your dApp, you have to put yourself out there in the open. I mean, let's take an example of Uniswap. If you were to deploy a DEX today, you will have to create some kind of legal framework to manage that DEX and follow the necessary compliance measures if you want a large amount of users to be interacting with your dApp. And similarly, from a user's point of view, in theory, you don't really need to reveal your real world identity to interact with the dApp. But as you'll try to do it more often, you will find that at some level or the other, you'll have to do some kind of KYC process. And in that process, you'll have to reveal your identity. So, again, there's some difference between the theory and the reality on this aspect as well. The next is censorship resistant. No single entity on the network can block users from submitting the transactions, deploying dApps, or reading data from the blockchain. This is there as it is. Like you cannot stop anyone from doing anything. Different kind of people do different kind of activities on the network. For example, many DeFi apps have deployed their dApps on the network. Many people use them for trading or other stuff like yield farming. Then there are hackers who try to hack these dApps, and then there are also investigators who investigate all of the blockchain data to essentially find out whoever hacked a protocol or did a rug pull. So it's really censorship resistant. Like traditional financial systems are closed. You cannot see all of the transaction history and all of the activity that is happening on the network. But on Ethereum, everything is public. So you can see the activity happening on the network. It's just that with the privacy aspect, for some of it, you might not be able to identify which real world identity is doing a particular activity. But then again, if I compare theory versus reality, there are well reputed organizations like Chainalysis, etc., which do a very thorough investigation of the overall activity on the blockchain, and they can easily trace the real world entity behind a particular Ethereum account. So, as with other points, the difference between the theory and reality remains. So, next benefit is complete data integrity. Data stored on the blockchain is immutable and indisputable thanks to the cryptographic primitives like public private key cryptography and consensus mechanisms. Malicious actors cannot forge transactions or other data that has already been made public. So, you'll recall this from our What Are Blockchains video as well, that once more and more blocks are added to the chain, it becomes really hard to tamper with the historical data of the blockchain. So, if you take an example of a centralized service, if someone really wants to tamper with the data, they can go and change the entries in the database. But with blockchain, you cannot change the history, that the transactions that has already happened, because with more and more blocks being added to the network, it becomes increasingly harder to tamper with the network. And then there's also this aspect of crypto economic incentives, where anybody who is trying to hack the network, when they will try to evaluate the economics of their activity, they'll realize that it would be much more profitable for them if they just try to contribute to the network instead of hacking it for their own benefit. The last benefit is trustless computation and verifiable behavior. So, smart contracts can be analyzed and are guaranteed to execute in predictable ways without the need to trust a central authority. This is not really true in traditional models. For example, when we use online banking systems, we must trust that financial institutions will not misuse our financial data, tamper with records, or get hacked. So, if you take the example of having a bank as a centralized entity, when you are doing transactions with that bank, you have to put your trust on that bank that they will send the amount of money that you are transferring to the respective account no matter what. But with blockchains, you don't really need to trust the dApp, because if you have a bank as a dApp on Ethereum network, you can actually check its smart contract code and you'll see the functions that actually transfer the amount from your account to the other person's account. So you don't really have to trust on anyone because you can just go and check the smart contract code. And since it's the smart contract code that is already deployed on the network, it will execute the way it's written. So any activity that you do on the network would be done in the way that is intended by that smart contract. So that's how you get the trustless computation and verifiable behavior of dApps. Now there are some drawbacks to dApps as well. Like they require maintenance. dApps are very hard to update and any security risk may cost a lot. So once you deploy a code on Ethereum network, it is essentially immutable, uh, because it is deployed as a part of an account address and you cannot really modify the code once it's deployed. First, you have to think a lot about what code you are deploying. In traditional software development, like Web2 software development, you can deploy anything, and if the bugs happen, you can push the update immediately. But with smart contracts, you cannot really update the smart contract once you have deployed it. There are some proxy methods, etc., which is a topic for discussion later. But in its raw form, you cannot really modify the smart contract once it's deployed. So if you deployed a faulty code, first of all, any hacker can view that code because it's publicly accessible. And second, they can really exploit it and you won't be able to do much because the smart contract is written the way it is and it will behave accordingly. So this makes dApps very hard to maintain, hard to update, and the security risk is also very high. Like you can go to this website, it is reg.news, and here you will see a list of all the hacks that have happened until now. And most of the hacks are in millions. Like you have a 6.8 million hack, you have a 304 million hack. So generally the hacks cost a lot and you cannot really do anything about it because you cannot change the smart contract. You can follow some standard best practices to avoid it, but the mistakes are very costly when it comes to dApps. Another drawback of dApp is performance overhead. dApps have huge performance overhead and scaling is really hard. To achieve the level of security, integrity, transparency, and reliability that Ethereum aspires to, every node runs and stores every transaction. On top of this, proof of stake consensus takes time as well. So you can only imagine all of the activity happening on the Ethereum network is stored by multiple nodes locally. So as the activity on Ethereum network grows, the amount of data that needs to be stored with these nodes would also increase exponentially. This is the reason why the concept of full nodes, archival nodes, and light nodes was brought in. Another drawback with dApps is network congestion. When one dApp uses too many computational resources, the entire network gets clogged up. Currently, the network can only process about 10 to 15 transactions per second. And if too many people are using the Ethereum network, you can see that a simple transaction of sending Ether from one account to another, which would cost anywhere between $1 to $2 normally, can go up to $50 to $100 in terms of gas fee. So that is a really major drawback. Some other layer one protocols have tried to address this, like Solana, which have a higher TPS than Ethereum. But again, they suffer somewhere in terms of reliability, that they go down very often. The fourth drawback of DApp is the user experience. An average end user might find it too difficult to set up a tool stack necessary to interact with the blockchain in a truly secure fashion. So, if you think about any of your experience of interacting with a DApp, let's take Uniswap for an example. If you want to convert one token from another, you first need to set up your wallet. You have to create a new wallet. For that, you'll have a seed phrase that you have to store safely. It shouldn't get compromised. You cannot store it digitally because their chances of compromise are higher. You have to write it on a paper and store it safely. Then you have to interact with a dApp. It could also be a malicious dApp, you don't know. You can also end up sending your tokens to a phishing contract, like someone who is impersonating to be a Uniswap contract. You can use a hardware wallet for higher security, but again, that comes with its own challenges. Like, if you compare interacting with a dApp to the Web2 experience of interacting with any application, you'll see a lot of difference in terms of user experience. Time and time again, it's proven that once the user is used to a certain kind of experience, a certain kind of convenience, they really go back on that. So Web3 has a lot to cover up in the user experience aspect, that you are creating better financial applications, but they are not very user friendly in nature. People are not going to move from Venmo, Google Pay just for the sake of a decentralized application. Dapps really need to catch up to the current user experience along with their own benefits to be able to actually replace traditional financial applications. Last drawback of dApps is centralization. Now, this is slightly ironical because dApps are supposed to be decentralized, but user friendly and developer friendly solutions built on top of Ethereum might end up looking like centralized services, anyways, because ultimately you won't see the difference between the current service or the dApp. At the user interface level, it mostly looks the same because the activities are going to be the same. It's just the backend is completely different. Web2 services execute on single servers while Web3 services execute on a distributed network of nodes. So the difference really lies in the backend and not the front end. So most of the dApps end up looking like centralized services anyways. And that's where the real drawback lies, because behind the scenes the dApp can use the centralized portion, like they can execute some important business logic on a centralized server, or they can store some sensitive information server side, and that becomes problematic for the ethos of a decentralized internet. This centralization eliminates many, if not all, of the advantages of the blockchains over the traditional model. So that was all about dApps. In the next video, we'll talk about accounts on Ethereum.